Next, we're going to talk about three special types of notation, asymptotic notations, which are related to the big O, big theta, and big omega. So, which are small o and small omega notations. Actually, we are going to talk about two of them. So this part is an optional material, optional content. So, but reading them will give you a better sense of how they are different from the big O and big omega. Okay, so the small o notation, it basically we can consider that the fact that the bound, for example, in this case, the quadratic function 2 times n squared. If we say that it belongs to the big O of n squared, then the n squared quadratic function is a asymptotically tight upper bound for 2 times n squared, right? But for a linear function here, we used this example before, right? For a linear function, the quadratic function is also an upper bound, right? But it is not a tight bound, okay? So in this case, when the upper bound is not a tight bound, we can use the small o notation to indicate the upper bound that is not asymptotically tight, or we say it could be a loose bound, loose upper bound. So the formal definition of small o is quite similar to that of big O, and the only difference is here. So the statement is that for any positive constancy, there always exists a constant n0 such that Fn is always below C times G of n. So this is a quite strong condition, because in this case, we want to show that the relationship will hold for all constants, not just some certain chosen constants. Okay, but we're not going to prove it in some using some concrete examples. We just want to compare it with big O notation. Okay, so big O says the G of n is the upper bound for some constants, right? But we just need to find some constancy that hold the inequalities. But for the small o, we need to show that the inequality here holds for all the constants, which is a very strong condition. Okay, so for example, we can say that the quadratic function is the linear function can be described by the small o of n squared, but a quadratic function cannot be described by a quadratic by a big O or by a small o of n squared, because if we have c equals 1 here, right, then simply we cannot find the n, the 2 times n squared is smaller than n squared for all the n's. Yeah. And so basically the small o notation means that the target function Fn will become very insignificant relative to G of n as n approaches very big values. So that's the small o notation. Okay. So if we use the limit language to describe, we'll say that because f of n is very small compared to G of n, so if n is very big, then the ratio of f of n over G of n becomes 0. All right. So that's big. That's small o, and then we can think of it. We can guess the meaning of the small omega, right? It must be deal with the lower bound. Okay. So its relationship to the big O notation is to the big omega notation is just as the way that small o is to big O. Okay, it denotes a lower bound that is not tight. So actually, or it's a loose lower bound. So it always use the statements like we need to find basically for any positive constants, we want to show that it is the C times G of n is the lower bound for f of n. And so using the quadratic function again as an example, we'll see that the quadratic function here, n squared over 2, is the small omega of n, because the linear function is always smaller than a quadratic function, as long as the n is big enough. But we cannot use the small omega of the quadratic function to describe the target function here. Okay, and use the language of limits. We can also show that because f of n is a very large function compared to the g of n, so the limit of f of n over g of n approaches infinity when n is sufficiently big. Okay, so here's some additional information about big O and big O, small o and small omega. And throughout the chapter, or throughout the topic of algorithm analysis, I would say that big O and the big omega and the big theta, they are more commonly used annotations compared with small o and small omega.